is Jacob Laatkamp from NLR, Netherlands Aerospace Center, and together with Patrick I will bring you this demonstration. We are a relatively small research group and we are specialized in non-destructive testing and mainly focused on aerospace, but we also do projects for other sectors. For example, we did a project on windmill blades to develop sensors to inspect blades on height in combination with drones and crawlers. So it's not always aerospace, but it's our focus. If you look at the first slide over here, it's a little bit the future. Sometimes you have terms like smart hangar, hangar of the future. We keep it a little because then you're inspecting complete aircraft. We are keeping it a little bit modest, and we are looking at component level. What we can imagine is that we have a calibrated window with all different kind of sensor systems, and you put in an aircraft component and it recognizes the component and it does the inspection which is required for that component. Keep this picture in mind, and with the demonstration I think you can imagine that the techniques that we demonstrated, you can imagine, oh, that could fit in such a concept. We did a project for DCMC, and it was in-service non-destructive inspection, and the objectives were the development of an inspection method for large-scale areas, so many square meters, and it should be a reliable NET method. It should be performed under MRO conditions. That means that it should be capable and the technique must be redundant in a hangar environment. And of course, the Development Center for Maintenance and Composites, we are focusing for these techniques on composites for this project, but you also can use it for metals. What is non-destructive inspection? Now, inspect or measure without doing any harm to your assets. That is the idea of non-destructive inspection. Do you want to find everything? No, because you will end up with a very expensive inspection technique. You want to find the minimum allowed defect, that reject criteria on that border. That is what you want to find reliable. Not everything, because then you will end up with a very expensive inspection method. And if you look for examples of defect types, yeah, for metal, obvious corrosion, cracks, inclusions. And if you look for composite materials, there you have delaminations, matrix cracks. And the last three, porosity, voids and dry fiber. Actually, they do not play a role during MRO. They are really good introduced by manufacturing, and also there you have NDI, and that's covered by the non-destructive inspection after manufacturing. So we are mainly focusing on delamination, which could be caused by impact, foreign object damage. What you also can do with the techniques that we show is to determine the geometry. Question? Yeah, you can always ask questions. Yes?
Because I do think that the other stuff could fall within the MRO, because if you have repaired the fuselages, then
yep.
after that you need to do an inspection as if it's...
Yeah, and then actually you have a very small manufacturing part where you can enter. Yeah, you're right. For repairs, you're right. Yeah, very good. Yeah. We didn't focus that on this project. We're really for delamination.
No.
Yeah. Very good. This is our concept. We have a component which has to be inspected, and at the left side we have techniques where we cover the external of the component. So we're gathering the 3D geometry of the component, and if there are surface deviations, we can also determine the surface deviations. And at the right side we look for internal damages into the composite material. And that is then the non-destructive part. In the middle, and it's really depending on your application, you can have an automation concept, and I will show you at the end of the presentation two concepts what we developed at NLR. And at the end you will have a full digital representation of your component. And we also show you examples of that.
Are you using any digital twin information?
Yep. We are an NET group, but other departments at NLR work at Digital Twin. We make corrosion logbook. It's an app that we developed at NLR, and because with these techniques you're generating data, and that's very nice and it's very good data. But but you have to, for maintenance personnel, you have to extract the correct data at the right moment. So yeah, we're thinking also about that.
I'm thinking of making baseline measurements on the lower lobe cavities of the 787, the cargo areas.
Yep. Zero measurement actually. Yeah.
Because it's very difficult to interpret the structures if you not know what you're looking for. So much information.
Yep. But if you in time do interval inspections, you have a baseline inspection, you do interval inspection, I think you can show that, and you do, for example, subtract. Can you do subtract data from each other and see the differences? We can show it a little bit in this demo, perhaps. I'm just looking at Patrick now. Okay.
We have to make an additional feedback. So
Okay. Yeah, but you have your cut now. You can show the difference. The first demo we want to give you is 3D structural light scanning. You have a lot of different type of techniques of gathering your 3D shape, laser line scanners and so on. This is working with stereo cameras, so you can see here the camera, two cameras with a certain angle and a distance between it. And in the middle we have a projector with blue light which projects a fringe pattern on the surface, and on basic of triangulation principle you can measure the point at the surface, and if you do enough acquisitions around it you have your 3D shape. This is a relative big one, 1 square meter field of view, but there are also smaller cameras available.
Okay. And even bigger ones.
And even bigger ones, yeah.
So I'll be giving the demo. So if we now focus on the other screen, you can see the results. And now I'm just positioning the camera in roughly the correct order. So this is a radar that we received from Fokker Services. We made some additional dents, etc., to be able to show this technique. Let me just rotate. Yeah. This one. So what it basically does is we have the two cameras, which I can show both images. So we have a right camera, left camera, and by using those two images, you can actually measure the surface. We've put reference markers on top of the radar because we take a single image and the next image we need to stitch together. So we need to know the position between images. You can either know the position of the camera or you have to have a common reference point. We use the common reference point in this case. Scanning is almost automatically, so I just need to, spot one. I just need to set the correct exposure, etc. And then I press a single button, and now it's doing the scanning. So now it has scanned this entire surface that is covered in blue light. The results are already shown over here. So this is already the scan of this entire surface. If I want to scan more of this component, I just move the scanner around. It will notice the reference markers. It will show you the box I'm scanning, and it can take another scan. It's working with the remote. So this is how we basically scan a component, just by moving the scanner around. You can also use, instead of me pushing this, you can use automation to do it. But we do a lot of different components, so we actually, we sometimes prefer to do it this way. But now that we have done the scan, we also of course want to know, what did we scan? what are we looking for inside of the data. I'll move the scanner a bit here. So what we can, for example, do is here we can actually already see the dents that are there inside of the model. But of course we also want to know the depth, etc. So therefore we can just simply go to the inspection part. We can select the area in which we want to know something. So in this case I want to know something in this area. And I can, for example, construct a surface defect map. So with this I can easily detect dents, etc. So that's there. It's always in 3D to get it properly aligned. Inspection. This one is not calculating. Estimate. So the method I'm using right now, it comes from the car industry, where they use a grinding stone. You move it over the surface, and if already you don't grind the surface, you can see there's a dent there. So this is basically the electronic version of that. So here it shows me the depressions of the surface. I can also show the mesh, and from this I can easily see the depth. So this depth is in micron.
Yeah. Do you also do you have the capability to indicate curvature
Of the
dent?
yeah, there is. Let me just check. For example.
No, it's, if you say
yeah, there is, but I need to
to
check
show
out.
too much. But
Yeah.
if you have hill damaging classic structures,
Yeah.
then beside the depth, it's also very important to know how steep that dent is.
I can actually make a cross section through the dent and show you. So it's possible to make a cross section and to see the curvature. And also to do values from that. So for example, right now I've made 2 points, so I can easily measure the distance between different types of dents, etc.
And for a certain inspection, one could think of a dedicated program steering this.
Yeah.
The distance, the depth, and the amount is determining if a leading edge panel is still useful.
Yeah, it can be done automatically. Also, the recording can be done automatically. So
we'll
this is
make an appointment, and then we'll see if we can do a leading edge inspection.
that's fine. Good. So this is then the point distance, etc. This is a component where we do not have a CAD model from, but we've scanned it before, so we can actually use it as a CAD model. So that's the blue one shown over here, and here we've scanned the entire surface. And from that we are able to actually do its deviation from CAD. So we can actually see what's the deviation from the first model that we've scanned. And now we can actually see that the extent of damage is also more than that we saw with this method.
I really think the technique of being able to compare, the comparison technique is very important for the accessibility of the information.
Yeah. So
here
here
you always see something.
Yeah.
But
and we can actually put also bounds on it so that everything becomes green and everything that is below a certain threshold becomes red, etc. So here we again have the same deviations that you can see, but there's also a bulge because we did an impact from the inside. So we can see all those kinds of things.
With the proper software, could you also be using images of a sensor, which has just moved around it, instead of having this installation.
And yeah, then you have two
That
images,
you use multiple images from different angles.
Yeah, but then
And then also with the same kind of angulation.
yeah, you can, but then you need to have enough anchor points on the surface.
Yeah, but you have your anchor points here as well.
If you have the markers and
Yeah,
you know the distance, then it is also possible. If you, for example, have a large fuselage, if I take a measurement 1 square meter here and then do it 2 meters from that, it's the same and it's impossible to match those.
Yeah.
So then you can also think of concepts where you actually track the scanner instead of...
Yeah, track the scanner.
Yeah.
How much smaller is this thing available? Because a square meter is very sizable.
Yep.
If you could go to 50 centimeters to 50 centimeters, would it now be something you can hold in your hand?
Yeah. It depends on the accuracy that you want to have.
So
actually,
the same accuracy,
actually
only a smaller area.
we also use this same scanner,
Yeah.
exactly the same stuff, different optics, to actually measure a smaller area
Yeah.
to get better accuracy and resolution.
I'm thinking in the following scenario. If you could combine the information you're measuring and calculating and have a projector aligned based on so now the person doing the scan can see the result directly in front of him. Now you could have that on the line where you have a small bump in the aircraft, stick this thing against it and directly have your measurements. And I do not need to call a construction specialist who comes from Schiphol East to do that measurement.
So what we can already do using only this scanner, it is, of course, it has a projector on there. So I can actually, if I, for example, now I've taken a couple of points and I can project them on the surface.
Okay.
So this is only a single color for now. So I can, I selected the dents somewhere in the correct area. We actually use this to apply strain gauges, etc. So if you have a CAD model, it's located on a CAD model on a different curvature, etc. It's really difficult for the operator to determine what's the location. We use this system, he makes a mark, and then he's able to paste the strain gauges there.
Cool.
So this is just a single position, but we can also, of course, we can do, for example, a surface curve. So I can also make a curve saying, I want to be able to repair around this section and project that curve on top of the surface.
Ga je een feestje van maken?
Of course, surface curve, those are not there. And then I can actually move the scanner around, and as long as the scanner knows where it is, it knows because of the reference markers, you can see that's still projecting the stuff.
The only thing I have with this setup is big.
Yep. Big but accurate.
In the shop?
Yep.
Like maintenance?
There's also the thing with stability. With stability, so if we do a scan, the scanner has to remain absolutely still, and will give me warnings if it's vibrating, etc. So if this floor is nice and even, it's fine. Sometimes when we do the measurements at home, the floor is not that even, and I actually have to fix the scanner and be able to measure something. So
actually, you can drive the camera around, but if you tilt the camera,
yeah, it's fine.
Yeah.
Because it's still,
During
it's not during the measurement. So during measurement it needs to be stable. So I can use it like this, and it's also...
which is going to be a difficult thing if you're going to measure my leading edge sled of 37. Because you need to be like 5 to 7 meters high.
Yeah, you need some kind of platform to
But how stable do you
to
need
have
to
it.
have that?
Depends on again on the accuracy that you want to have, and on the amount of light that we can use, because there are also systems that have more powerful optics, and they use laser light, and then you go to really short shutter times, and then if the stuff is vibrating and you still have the markers there, it's fine. if your part is also vibrating, you also lose accuracy.
What's the time frame it does its measurement in?
For this case, I can see the single shutter value is 40 milliseconds. It takes a couple of pictures, so you have to have it stable for a second or two.
If you do not do calculations in between.
You mean a single snapshot? Or?
No, if it's 40 milliseconds.
Yeah, it's a single picture. It's a single picture, but for every pattern that it takes a picture, of course. So if I do the measurement, 1, 2, 3, 4, 5, it's already 5 pictures. So in this time frame, it has to be stable.
Yeah, if I understand.
Yeah.
Unless you decouple them and do a new distance measurement and then take a new picture and then calculate it in your computer.
Yeah, it's also possible. Yeah. But for example, if I want to do, can you move the scanner, touch the scanner a bit? So if I now do the measurement, it's shaking, etc., it says it can do a measurement. It actually waits until it's stable and then it does the measurement. And now it says the movement is too high. So it's still vibrating. I can still use this measurement, but I will be less accurate in the results. So it also depends on the accuracy that you want. So right now the accuracy is 15 microns. So if you don't need that kind of accuracy, you can...
50 microns is extreme.
Yeah.
Extreme, yeah.
Yes.
That means that if you reduce the resolution, then you have more redundancy to vibration.
Have you tried a thing like that on a cherry picker? I hope that cherry picker up.
But you then can of course also think of stabilization systems.
Yeah.
So
yeah. But then it's becoming heavier and heavier, you know.
it all depends also on accuracy that you want. So you can accept the movement. And if you don't need to be accurate within that movement, yeah, you don't care that it's moving, and then you can do the measurement.
Because I know that the hill limits to those aircraft, I don't know about the 778X, what type of leading edge panels that one will have, if it's going to be full composite. Because composite is so much more resilient to those hailstones. But the aluminum panels, if they have too many dents, then it needs to take off, and the sheet metal workers really take a long time to measure those things. And that has to do with the position, you know, you almost drop off the wing when they have to measure. So they have this harness and fixed to the wing, but still as a human you kind of loop, you don't want to fall down. So it takes several hours to decide if the aircraft can fly or not.
Yep.
So I can imagine a thing like this being moved over the wing, taking its pictures, and maybe have a decision go or no go in half an hour.
Yep.
That's a business case.
Jacco will show you automation concept for that, which we're already working on. So.
Okay.
Yes.
Yeah, this was the 3D demo.
3D demo. We go now through non-destructive inspection. So this was the external, and now we're looking into the material. And we have several techniques at NLR. We also do what we call so-called multi-domain because one technique is better in detecting a certain defect type than another, and if you combine them, you have a very good data set. We only show you today lock-in tomography. At the left side picture you can see the setup. We have an infrared camera standing over there, the blue one. We have 2 halogen lamps, and with the halogen lamps we bring in heat into the material.
How did you hold on?
Sorry?
What's the name?
Hello,
Oh,
Halogen lamps, yeah. Yeah. And you can see here the halogen lamps, and we bring heat into the material. Actually, it is a real composite material. It's a CT scan, and you cannot see it from that distance, but there is a real delamination over here. And what's happening is the heat will flow into the material, and actually where the composite layers are disconnected to each other, this delamination, it will block the heat flow. And you get an accumulation of heat above the defect. And actually that will give you a raise in temperature of the surface. And that's only millikelvin. It's very small temperature differences. We modulate the lamps, you will see it in the demo. First we start with high frequency. So they are modulating high frequency, and we bring in relative less heat. And this is this picture. And then we are more sensitive for surface defects and defects just below the surface. Then we reduce the frequency, bring in more heat, getting more penetration depth, and if we reduce it a little bit further the frequency, we get a full capture of the thickness of the part. What are the advantages of this kind of technique? It's fast. Also, this camera is approximately 1 square meter, the field of view, so one acquisition you capture 1 square meter. And that was the objective, large area scanning of composite material. There is also a downside of the technique. I think if you inspect composites, then ultrasonic is actually the workhorse. You get a very good data set of your component. But there are disadvantages. Example, after manufacturing, if you have a very large fuselage and you have to scan it ultrasonics, they are standing with Airbus, with Boeing, with Fokker. You have to inspect them, and they make a scan movement, a meander scan, index to 3 mm maximum, max speed on very large surfaces, 500 mm seconds. It takes sometimes 12 hours to inspect a component. So it's really sometimes if they ramp up the production, NDI is always the bottleneck. And that's ultrasonic, which is the bottleneck. And the equipment is relative high cost of investment. So the data set is less accurately, but it's much more faster. So it's really depending on your requirements, what is the minimum defect size that you want to find, and if you can do it with this technique, then it can be very cost effective to the more traditional NDI techniques. There's another limitation, and that's the penetration depth. If we do it one-sided, in this case, for composite material we can go up to 4, 5, 6 millimeter, and that also depends on the defect size that you want to find. How deeper you go, if you have very small defects at a high depth, then it will be difficult for this kind of technique. Okay. We had a setup at NLR. We made photographs. You can here see the example of 3D scanning. This is the login thermography. The demo you will show also here. But I'll show you this picture because you can also do a through transmission technique with thermography. We also know that from ultrasonics, and what we do here is we put the lamp inside. And then the heat will flow through the material. And the benefit of this is when can go to larger thicknesses of material. But you need two-sided axis. If you have only one-sided axis, it's no option. Other technique we have is laser chirography. It's not demonstrated over here. What you can see here is you still have the same halogen lamps, and in this case they only pulsing one time, and we bring a thermal load to the material. We have laser diodes which bring a fringe pattern on the material. We take a zero measurement, then we apply a thermal load, and then you get an out of displacements of your surface. And you take a second picture or a film over time. If you have a defect, you get a little bit more out of surface displacements than a non-defect. And that's a very good technique for honeycomb materials. If you have a skin and you have the honeycomb core, and it could be Nomex or aluminium, doesn't matter, it's a very good technique. That kind of defect type you cannot find with tomography. because that gives you, if it's disconnected, it will give you no temperature differences. But with chirography you can find that kind of defects.
So is there a minimum thickness related to these technologies? Like a minimum?
Yeah, but if you look at sandwich materials, most of the sandwich materials, that's the whole idea of a sandwich. They have very thin skin.
Yeah.
Yeah. It's very good possible. Yeah, and it's very nice because it's non-contactive and they are very fragile. So if you can keep away with your NDT system and not in contact with that kind of solar panels, it's very convenient. Yeah. Rough order of magnitude times of the inspections. If we did it at NLR, it was then positioned at a turntable, so a little bit more convenient. We did it by hand, and these are the acquisition times. So for every technique, it's relative fast. Okay, we have a demo.
There's an evaluation in the heat up and in the ramp down.
No.
Oh, it's only the heat up?
Nope.
It's the cooling down.
Nope.
Okay.
It's not the podcast with the papagaai.
We use a lock-in technique,
Yeah.
which I will demonstrate in a moment. So we use a sinus form on the lamps, and we actually look at phase differences between the lamps and the surface. So with that, we are not sensitive to changes in emissivity, etc., etc. We can almost neglect for that, and we look at those phase differences. Because also by positioning the lamps, I'm just placing it right here, I will probably heat up the center more than I will do the outside. This is something that you see in intensity, but the phase difference will be the same. So it will give you an overall better image. I almost can't see the screen because of the reflection. This is the live image, so you can see I'm walking here. You can see my reflection also in the radome, so I'm going to actually move away when I do the measurement. We're going to do a measurement at 3 different frequencies, high, medium and low. So this is the high one. For high frequency we inspect the upper part of the skin. And if we go to lower frequencies we look more inside of the material. So right now this is the frequency where we really look at the top level of the skin to look for defects over there. This is the face image. So it takes the face of the lamps and the surface and gives a value and makes a grayscale value for that. So there's way more information in this image than I'm showing over here. But what you can see is we can see also the markers that we put on there. And we can actually use these markers to take this 2D image and map them on the 3D image of the scan that we just did, which is also what we're going to show. So this is the measurement at high frequency. We can take any number of cycles that we want. So if we take 1 cycle, we have a lot of noise. If we take more, we can actually reduce noise. So the amount of cycles that we take depends on the amount of the quality that we want to achieve. So this is a cooled camera. It's expensive but a good camera. So we don't need that many cycles. If you go for cheaper cameras, you need more cycles to get the same image. Even if you go to cheaper cameras, 1 cycle of this one will be better than 100 of a cheap camera.
If you say expensive?
50-ish. Yeah, if you go to higher resolution, it's around 100. So then you need to have the acquisition system also, lamps, etc. So another 50k. Yeah. And now it's done measuring. The results are on the screen. So what you basically would expect from a radome, it's basically in this case the same material. You don't expect to see any major differences. But if I tune this grayscale value a bit, I can see that we have some patches over here. So something is wrong over there, or at least there is something different there. We still need to figure out what. So if we go deeper, this is the deepest frequency to the same area. We can actually see that there's an entire patch in this area behind us. This is something that we cannot see from the 3D scan, because the surface is still intact, it's the same, it didn't change, but from the back there is something different.
Could you now show the lens we have seen before?
You don't have to move the system around.
Oh, okay.
We can do it after the demo, it's fine.
Let there is a repair. I'm kind of hoping it's somewhere in the neighborhood.
Yeah.
So what would be the deployment of this system in a shop to have first a look at it? Or?
The first screening. So for example, there is no delamination inside of the skin. We actually tried to make that using impacts and we didn't succeed. But if there was a real delamination inside of skin, the tomography will be able to catch that. So you know more the type of damage that's already present. You can have, of course, have a dent, but you don't know if the dent is also causing damage inside of the honeycomb, damage inside of the skin, cracking of the skin. And with tomography, you're able to better classify the defect.
If I would take just a picture of a carbon panel, or the skin of the 787, what would you be able to see then, other than manufacturing defects that it's...
The contrast in this image is also based on the amount of material that is present. So you would actually be able to see thicknesses of the material, depending on the thickness, because there is a penetration limit.
So what I would be looking for is if we drive into the aircraft with one of the loaders. The stupid stuff. The paint is very flexible, so it goes like boom. It's there. You see a black white on the aircraft. You don't know. Would this technology be able to see cracks, illumination inside the structure?
In this case, it will only be able to see where the paint has been detached from the surface. Because once it has detached, no heat will go through deeper layers, but you can identify there has been an impact over here, and my paint is not touching the surface anymore. If you remove...
I don't think that the paint is even detaching, it will stick to the...
Oh, if it sticks together, you will find the delamination.
And a crack? Would you see a crack in it?
A crack depending on the size, because tomography it's low resolution, so you're limited in resolution. But I showed you the radome yesterday, and there we can see the cracks in the paint and also in the skin.
One of the things in the MRO is moisture detection in radomes. Old-fashioned techniques are used radar moisture meters from the inside. How easy is it to equivalent this? So there is an acceptable threshold. But due to since you now render out the position of the eclipse, does that make it possible to make a threshold acceptable or not acceptable?
Yeah, because the phase difference will depend on whether there is water in there or not.
And it will not depend from, I expect that there is mold repair on the inner or outer skin of this radar. That is affecting the inspection. But could that be rendered out of the damage evaluation, of the moisture evaluation?
It will be more difficult to separate. That's why you use multiple frequencies, etc. And you can do the separation a bit better if you do not look at a single frequency, but you look at more. But these are the phase images, but you can of course also look at the amplitude, etc. And if there's water there, water is way more difficult to heat up, and you will see a dark spot in the amplitude image. So there are multiple ways to interpret this data. I'm just showing you one over here. So yeah. So Jaco, if you will do the switch again.
Okay, actually the same as what Patrick showed to you. Different kinds of data set we have. Another example, I think it is a mid-flap of a Boeing 747. It has approximately a length of 7-8 millimeter, and in the top you can see the free optical techniques. And here you can see the data set, the mesh, the point cloud, the surface mesh, a certain threshold on it to see the dents. Here you can see the tomography. We also put it in our ultrasonic C-scan, so we also have an ultrasonic data set, also 3D mapped on it, chirography, and also standard HG photographs on it. And here you have to be a little bit closer. Here is a repair. You see the repair in tomography, you see the ultrasonics, and you see that it's very nice stitched to each other. So it's a very convenient technique. Two automation concepts for this. At the left side we can see RB, and RB stands for Automated Rotor Blade Inspection. We developed these techniques for there are glass fiber rotor blades, and here you can see the rotor blades are not in there. You can see here the wings of a small electrical aircraft at MLR, Pipistrel. There are for carbon layers. You have to imagine that we have to turn this one 90 degrees, as you can see on this picture. And here you can see our tomography camera, chirography camera. You can see the helical lamps, and here the 3D optical light. It's a completely automated system to inspect a rotor blade of 9 meters length. And at the moment we are integrating the sensor systems that they can talk to the robots. It is intermittent inspection, so we do 1 square meter, we do all the techniques, we go to another square meter. But at the rotor blade near the root, we go to the tip, we also have differences in thickness of the skin. So we also learn the system that if, for example, if a further with the root being used, then the lower frequency. So in the end, we are now very busy to integrate and have the connection between the robot and the data acquisition systems. That's one concept. It's quite far. And the other one, it's also in development, another project under DCMC, where we use AGV, an automated guided vehicle, and a cobot, and you can see our tomography system. This is more for one application. This is more generic automation solution concept. Now we come to aerospace. It could be different for other sectors, perhaps a little bit more easier. But if you want to go from aerospace from method A to B, you have to do something. And that's called qualification. And you have qualification and certification. We talk about qualification, and first actually what we do is based on a user case, based on engineering judgment, we will say, can we use these optical techniques? We know the boundaries, we know the disadvantages. If you come with composite specimens of 10-12 millimeter thickness, we cannot inspect it, of 50 millimeter thickness. You need another NDT solution. If we think we can do it, we do a feasibility study, and then we look also for the requirements for that inspection. If we have to find a 3 millimeter square defect, which is very, very small, then we already know we cannot find it with those defects. So we look to the specification. It is doable with this kind of techniques. Then we develop this alternative inspection. And actually what we have to do is, we have method A and B, and we have to prove equivalency. We don't have to be better. We must have the same, we have to fulfill the requirements with the technique, and that's what we have to prove. Before we start execution of qualification test, we also have to look at conditions which can influence the test. For example, if this part is lying outside, we bring it in, we get condensation, then tomography will not work. So now you can do a lot of tests to see how much condensation would be on the part, which when one is influencing, when not. But you also can say, okay, the test to settle for several hours, that we 100% sure know that we don't have condensation. We have human factors. We have an application that we have replacements of tap testing. If you look at tap testing, then the human factor is very important. You need a lot of inspectors to see what are the differences of tap testing and to know what is the probability of detection of your technique, how good and how reliable you can find that defect, minimum defect which you have to find.
So do you take the spread of the human factor, do you take that into account to be able to set a standard for your new application, which might be an improvement on the lower end of your unit?
Yeah, because if you look at automated concept, then there is also a certain amount of human factor is always in there. But if you automate it, the human factor is much less. So, and then you have to talk with OEMs and you say, okay, human factor, we do automated, we do repeatability tests and so on and so on. Is this a point that we have to take into account in the qualification concept, or is it so far automated that we can reduce it?
And the OEM about that?
Yeah, we talk to OEM.
Okay.
For the rotor blade inspection, we are at the beginning, but we are in contact with the OEM. Yeah.
Because I'm challenged with the same, same principle.
Yeah. And
I'm looking at NDT ultrasonic inspectors.
Yeah.
And it's to me, as a non-inspector, NDT is kind of weird to see the spread among operators, and even on the instructions of the inspection.
Yeah.
Because if I have this area with small 1 centimeter blocks, where are you going to measure? So one took it upon himself to measure everything and take the lowest value. Another said, well, no, I'll take the mid position.
Yep. There are a lot of differences in the welding industry. I think it was in the 90s, they did a round robin test in Europe, and all test results were a lot of inspectors, different companies on welding, and they were shocked about the differences in outcome of the
So
NDT.
that's positive for automating stuff.
Yeah.
Okay, cool.
Qualification, we make reference specimens with known defects in there, so we know the size. We do a lot of data on it and environmental, but for example for automation you can say the outlining. It's not very critical with these techniques. If you have ultrasonics, then the outlining is very critical because you have to be perpendicular, and if you are a little bit 1 or 2 degrees out, you can stop with your inspection. This is very user-friendly for that. But you can imagine if you go to further that for example the alignment is still an issue. Yeah, so you do inspections 100% perpendicular, go 1 degree offset, 2 degrees, and you see what does that do to my detectability. Now, you can imagine more factors that you have to identify, and that can be different per NDT technique. And then you have one score, you know the defects, you detect them, or you miss. Hit, miss. And if you have enough data, you can fit a curve, it's all statistical. And for aerospace, we are aiming for, we want to have a 90% detection score of the minimum defect. But there is another effect, and that is called the confidence level around it, and it should be 95%. And these are these dashed lines. If you want to say from now it's very expensive qualifications and I have less data points because it's cheaper, then this confidence level bound will be greater. That means you end up with a minimum defect which will be larger that you can find reliable. So if you have a requirement, let's say 1 square inch delamination we have to find. And you know with this system you can find a ½ inch, so you have a factor more that you can find. Then you can make a choice that you make less data points because you already know, okay, I will meet the requirement. So yeah, but it's a difficult road, definitely.
Ask the student to take a look at the certification information, ISO, NIST, IASA, FEA, the OEMs, your own DOA and Part 21 guys. So you would like to what's your incentive as being to go the OEM route? Because if you now have an okay on those rotor blades, which can be a business case in itself, I completely understand, but it kind of chokes off the other possibilities, because then you need to start all over again.
If you are, for let's say, if you are with, I think if you, let's take the example of rotor blades, but you have different OEMs, and I've done it with one OEM, and I have qualified the complete inspection. I go to another OEM, we have to start again. I can imagine if you have the same OEM and you have a user case and you went through the engine code for another user case and you see parallels to that, perhaps it will be easier. But for us, as I already told, we are in contact with the OEM, but we are in a starting point, and for us we are very curious how that process Yes.
We had a very good measurement, 3D measurement system.
Yep.
We measured a flap of a 330, which we got rid of, and then the new client said, lots of things in this flap. We went, yeah, it's a used aircraft. Yeah, I want to know. So we made a 3D measurement of it, sent it to Airbus. You would make a caliper in the ruler.
Yeah.
It just didn't accept it.
Yeah.
So maybe it's wrong, but I'm thinking the other way around. The caliper, isonorm, NDT, isonorm, list. Try to build from there, and then go to the EASA. We have stuff, and then go to the OEM.
Yeah.
The other way around.
Actually, you're saying you want to prove equivalency. That's actually what you're saying, and that's also what we do. We try to do equivalency compared to the prescribed method, because there is already an NDT method. Otherwise, you will not develop a new one, and there you want to check it. And yeah, you can also. What also a possibility is we already said that for delaminations, ultrasound actually is the workhorse. You can also imagine in the qualification process that you go for a better NDT method, that you know you have a better data set, and also bring that into your qualification. That could also be a possibility, but we have to find a way. And also there, is it still cost effective? Also, yeah. What is a good approach? Yeah.
Yeah, you can imagine that your OEM is a little bit more approachable with Boeing.
Yep.
Very different.
Yep.
Same with Windows.
Okay. Yep. Yep. Perhaps we can help each other. Yeah. Are there more questions? Oh, it's not free dating. Okay.
So these are all the results from the measurements that we did. We now have a complete 3D. We now have a complete 3D model. This is the fluid transmission tomography that we did, and here you can see the repair patch again, but now more clear than from the lock-in technique. You can see that we use two different kinds of markers on the surface. We have the round rounds, which we use for 3D scanning. Those can be detected and identified because of those position in relation to the other ones, because it can measure in 3D. For these ones, I'm going to use the camera with the 2D camera, and therefore we use encoded markers. And then it knows where it is from those encoded markers in a 2D setting. So I can now switch on the augmented reality, and it will give me, if I hold it steady, it will give me an overlay of the data. So if you only want to use 2D images to do something, then you need, for example, encoded markers to be able to position your pictures. And this is then for the through transmission. For the lock-in that we did, we can do the same stuff. So it's all inside of a single program now.
En hier kun je dus nog die deuken ook overheen.
Hier kan ik die deuk ook nog overheen leggen. Alleen dit is de oude scan die wij op het NLN hebben gedaan. Dus die deuken die hierin zitten, die zitten er niet in.
Maar het is gehoord op de mogelijkheden.
Ja.
Dat kan handig zijn om je repareerbaarheid en evalueren.
Ja. Ik zou kijken, ik heb hier wat deuken in zitten, maar er zit weinig in. Ja. En dit is ook deze scandata hebben wij gebruikt als CAD-model om het verschil met die deuken uit te geven. Dus we hebben ook heel veel discussies met de OEM. Je scant iets, CAD-model heb je toch niet, dus je gaat gewoon kijken naar de delta's. Dus je scant hem de eerste keer in, de tweede keer als je langskomt, scan je nog een keer en dan kun je beter de delta's uitzoeken. We gebruiken zelfs deze scanmethodes ook voor reverse engineering. Dus je hebt een onderdeel, je wil hem eigenlijk namaken, je scant hem in, dan weet je de vorm aan de buitenkant, je kunt een beetje binnenin nog wat andere dingetjes kijken en dan kun je dat doen. Als we helemaal iets ingewikkelds hebben met echt kanalen aan de binnenkant, etc., dan kunnen wij een buitenkant scan van een 3D-scan combineren met een CT-scan. En die inderdaad ook overlayen om ook zo de binnenkant te kunnen zien. Afhankelijk ook van de dikte, etc. Ja.
Dat ook in deze scan of printen.
Ja.
Ja, maar ik denk dat dat dus aanvullend met lithografie kun je dan nog informatie extraheren over de skindiktes lokaal of veranderingen.
Dan zal ik bijvoorbeeld op augmented reality 4% met bril nodig voor het iPad. iOS is heel sterk, dat is
En wat wij ook voor de toekomst aan het kijken zijn, is we hebben nou, ik heb laten zien, we kunnen ook dingen projecteren. Dat is nou in kleur. Eigenlijk zou ik hier gewoon een rectie neer willen zetten en deze resultaten die we hier nou zien, projecteren hierop. Dan kun je het aanwijzen, je kunt gaan voelen, et cetera. Dat zou in een shop-omgeving meer gaan leveren, denk ik, dan...
Dat wil ik er straks uit. Line maintenance environment is very handy to have a quick assessment of land. Assess 787 skin, if it's delaminated or not. You know, it's an old setting, how much money, but in our aviation industry, it's really money. You know, how quickly we can decide that the aircraft can fly or not. The more we have possibility to reroute other aircraft, and it's really in the thousands of dollars.
What we can also do with, for example, with the demography data, I can overlay the real live stream with the measurement I did, and because I'm hot, I can just point to the stuff I can see on the screen where I'm pointing, and now here's the defect.
You can actually
mark it.
Yeah, you can also mark it that it is automated, that it's a 2-inch diameter indication.
Yeah, we can measure those in the software. We can import the data into the 3D model and do the measurement, or we can do the measurement on the 2D data, but then we need some kind of reference inside of the image.
And then you can export it in order to communicate.
Yeah. So if you have a flat surface going 2D, it's fine. If you have a curved surface like this, we will actually import it into the 3D scan to be able to better get an
accurate result and measure along the surface.
Yeah, along the surface. Yeah. Any more questions?
Super bedankt.
Ja, thank you. I think there are drinks.
Ja, mooi.